Hello, statistics students. In this video, we're going to finish the learning outcome on probability by learning more probability rules and tools that you can use to visualize probability questions. Our first topic today picks up where we left off in lesson 3.1 on probability rules. In the last lesson, we learned what the probability words or, and, not, and given mean. Today, we're going to use those terms to develop more in-depth probability formulas, where we actually have some formulas for various probabilities that you can calculate. With these rules, you'll be able to solve any type of probability question. So the first specific rule we're going to look at is for the rule of complement. The rule of complement is related to the probability term not. Not was used for opposite, and we represent the opposite of an event with the prime symbol on it. So not A would be A prime. Because one of the fundamental probability axioms states that when you add up all the probabilities in a sample space, they have to add up to 1. So what this means is using these two facts, we can say that the probability of an event A happening is 1 minus the probability of an event A not happening. Alternatively, you could also say the probability of A not happening is 1 minus the probability of A. These are two different ways to state the rule of complement, and it's using the fact that the whole sample space has to add up to 1 or 100% probability. If we take away the probability that an event happens from that 1, you're left with the probability that it does not happen. The rule of complement is essentially created to help you speed up your answer in very specific questions. So I'll give you a couple examples so you can see how it speeds things up. So the first one is, what is the probability of not rolling a 4 on a 6-sided die? We know the sample space is 1, 2, 3, 4, 5, and 6 for rolling a fair 6-sided die. If we want to find the probability of not a 4, so I do 4 prime to mean not 4, the rule of complement says you can find that by doing 1 minus the probability that you do roll a 4. The probability of rolling a 4 is only 1 out of the 6 options, leaving you with a 5 out of 6 chance. The other way that you could have done this is look at the sample space and look at every single number that's not a 4. There's 5 that are highlighted in the blue. So you could have also done 5 out of 6 by looking at all the events that are not a 4. Or you can use the rule of complement, 1 minus the probability you do get a 4. Both answers give 5 out of 6. This next one will really show you how the rule of complement can be faster in some situations. The Toronto Maple Leafs have made it to the playoffs, which are best of 7 games. The probability they sweep their first series is 0.744. Let A be the event the Leafs sweep the series. So what that means is the teams normally have to play 7 games in a row. 1, 2, 3, 4, 5, 6, 7. Sweeping would be they win the first game, win the second, win the third, and win the fourth, and then they stop. They don't even have to play the last 3 games because they won the best of 7. So if they win 4 in a row, that's what a sweep means. So what is the probability of A sweeping? The question says that the probability of sweeping is 744. If A is sweeping, not A is not sweeping. So not A is not sweeping series. The problem with not sweeping the series is that this could happen in so many ways. It could be win, 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 lose, win. It could be win, win, lose, win, 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 lose, win, win, win. It could be win, win, lose, lose, Win-win. There are so many different combinations of the events. And in this case, order of the wins and losses do matter. So they are, in fact, permutations. But the reason that this is very tricky is because it could end if they don't sweep after 5 games, or it could go all the way to 7. The only way they do sweep is if they win 4 in a row. But if they don't sweep, it could end at 5 games, or it could go all the way up to 7. So you'd have to figure out all of those combinations and find the probabilities of them all. The rule of complement makes this question a lot faster because if you want to find the probability of not sweeping, according to the rule of complement, it's just 1 minus the probability of sweeping, that they're opposites. So 1 minus 0.744, when you take that difference, it's 0.256. That's way faster than looking at all these different combinations or permutations in this case, because order matters, and trying to find the probability of each one. That'd be a very slow process. It's not quick like here, where we can see that there's 5 that are not 4s. So the rule of complement really does speed this one up. Just 1 minus the probability they do sweep gives you the probability that they don't sweep, that they lose at least one of the games or have to go to 5, or they could go all the way to 7 if they don't sweep. The next rule we're going to examine is the addition rule in more detail. The addition rule was associated with the word or, and when we first introduced this in the last lesson, we understood that or means it could be in A, it could be in B, or it could be in both. It's any of those. In order to apply addition rules with the word or properly, you need to understand what the word mutually exclusive means. Mutually exclusive is a term in probability that means that the events cannot occur together. Another way of saying that is the probability of A and B is 0, or the empty set, where again this intersect symbol means and, that they happen together. So the both probability would be 0. That's what mutually exclusive means. They can't occur at the same time. The reason that this is important is because if you do have mutually exclusive events, then the probability of A or B occurring is simply probability of A plus probability of B. However, if you have events that can happen at the same time, another way of saying that is not or non-mutually exclusive, then the probability of A or B is probability of A plus probability of B minus the probability that they happen together. The reason that you have to subtract the and probability is because otherwise you would count it twice. If they can occur at the same time, you would count when they both happen within A, you count when it happened within B. And you don't want to count the probability twice or it won't add to 100%. So how we solve that is we subtract where they both happen. So we only count it one time, not twice. Okay. So let's do some examples that will use the rule of addition to help us practice. So a card is drawn from a standard deck. Let A be the event drawing a 3, B be the event drawing a heart, and C be the event drawing a 5. So first, what are the individual probabilities of the events? So if A is drawing a 3, there are 4 3s out of 52. If B is drawing a heart, there are 13 hearts in the deck out of 52. And if C is drawing a 5, again, there's 4 5s. 5 of hearts, 5 of diamonds, 5 of spades, 5 of clubs out of the 52 cards in a fair deck. What is the probability of A and B? That intersect symbol means and. This is asking you for the probability of a 3 is A and a heart. So to be both a 3 and a heart, there's only one way to do that. You get the 3 of hearts, 1 in 52. Then the probability of A and C. That one's saying 3 and 5. Can a card be both a 3 and a 5? No, so that's the empty set. Another way of saying that is those two events are mutually exclusive. They can't happen at the same time because you can't get a card that's both a 3 and a 5 at the same time. Now let me show you how these ands probabilities, when you have mutually exclusive, they can't occur at the same time, versus not mutually exclusive, they can occur at the same time, and how that influences the rule for finding or probabilities, A or B, A or C. So for A or B, basically what that one's saying is 3 or heart. So that would be all the threes. There's four of them out of 52. All the hearts, 13 out of 52. But the problem is, when we calculated all the threes, we included the 3 of hearts. Then when we calculated all the hearts, we also included the 3 of hearts. So to not double count it, if you have non-mutually exclusive events, the rule says you have to subtract the probability that they both happen. So they both occur. When you get the 3 of hearts, you have to subtract that probability so you don't double count it. 4 plus 13 would be 17, minus 1 is 16 out of 52 is now the probability. If you want probability A or C, that's saying 3 or 5. There's 4 threes, there's 4 fives. They can't happen at the same time, so you can write subtract 0, it doesn't influence anything, or you can just skip that step because they cannot happen at the same time. They're mutually exclusive. You don't even have to subtract the difference because they cannot occur at the same time. And that probability of a 3 or a 5 would be 8 in 52. So this shows you when you have not mutually exclusive events, you have to subtract the probability that they both occur, the and, or you'll double count. If the events are mutually exclusive, you can simply add them up, the two individual probabilities. That's why it's called the rule of addition, because you are adding the probabilities. The last rules that we're going to look at today are called multiplication rules. Multiplication rules go with the word and in probability. When we were looking at the addition rule, there were two versions based on if A and B were mutually exclusive or not mutually exclusive. The multiplication rules have a similar idea where multiplication rules will depend on if your events are independent or if they are dependent. So just like mutually exclusive influence the formula, for multiplication rules, independent or dependent will influence the formula used. So independent means the probability of one event does not impact the other. Think about flipping a coin. Just because you got a head on the first toss does not mean you're more likely to get a tail or another head on the second toss if the coin is actually a fair coin. Flipping a coin is supposed to be random, so one option or event is not supposed to affect the next. The same thing is true with rolling a die. Rolling a die is supposed to be independent because if you get like a 6 on the first roll, it's not supposed to change your second roll as long as you're using a fair die that is not rigged. One thing that does influence independence is if you sample with or without replacement. With replacement means that you replace an item. Think about picking names out of a hat. If you pick the name and then you put it back in, then your events will be independent. The reason for that is if you put the name in, you reset the hat so it's the exact same with every single pick you do. Without replacement is the opposite. Let's say you pick one person's name to win a prize. Once you've picked them, you do not put the name back in the hat. This actually creates dependent events, and the reason is once you take one name out, you've changed the number of names in the hat, so your second pick will depend on the first one. You won't be able to get the same person twice. There are some ways you can show if events are independent, and these are related to your conditional or given probabilities that we discussed last class. If the probability of A given B is equal to the probability of A, then the events are independent. If B given A is equal to probability of B, they're independent. And then if probability A and B is equal to probability of A times probability of B, then they're also independent. If you don't know if the events are independent, assume they're dependent until you can prove otherwise. Once you have determined if the events are independent or dependent, this leads to two versions of the multiplication rule. If you have independent events, then we can say that the probability of A and B is simply A times B. However, if you have dependent events, then the probability of A and B will be the probability of B times the probability of A given that B already happened. Okay, so let's look at some examples to help you understand these rules and how they apply. We'll talk specifically about if we have independent and dependent events to help us with these questions. So first, what is the probability of rolling a 3 on your first roll and rolling a 4 on your second roll? Rolling a 3 versus rolling a 4 are supposed to be independent events if you have a fair die. That means the first roll should not influence the second roll. If that is actually true, then we can say that the probability of getting a 3 and then getting a 4 is simply the probability of a 3 times the probability of 4. That's why it's called the multiplication rule. You simply multiply them. Probability of 3, 1 in 6. Probability of 4, 1 in 6. We would get a 1 in 36 chance. For another question, what is the probability of drawing a king, replacing the card, and then drawing a queen? We said that when you have with replacement is telling you the events will be independent. When events are independent, that means you can simply multiply the probabilities. You're allowed to just straight multiply them. So probability of king and a queen will be probability of king times probability of queen. We can simply multiply because of the with replacement. And we know there's 4 kings and 4 queens. 4 times 4 is 16. 52 times 52, you might want to use a calculator. And it's 2,704. So 16 over 2,704. You can calculate that in Excel if you would like as well to see what number that is. It's about 0.006, so 0.6% chance. Now, what if we have the same question but without replacement? We said that when you have without replacement, then the events will be dependent. So this is our first circumstance where the events are dependent, and according to the multiplication rule. When events are dependent, then the probability of A and B is the probability that B happens times the probability of A given that B already happened. I'll show you how that influences this question. So the probability of king or queen, or and queen, sorry, without replacement. This will be the probability that you pick the queen times the probability you pick a king given you already took the queen out. Or I guess we can reverse it because the question says probability drawing a king first. So I'll just reverse it because it says that the king is first. So how this would work is probability of king times the probability you get a queen given you already took the king out. So with the first pick for the king, there's still 4 in 52. Then what about this probability? The given. How do we find the probability of a queen given you've already taken the king out? Well, if you take the king out, how many queens are still left? 4. The first card was not a queen, so there's still 4 queens left in the deck. But if you take the king out, how many cards in all are left in the deck? There's only going to be 51 because you took one king or one card out. And that's how we calculate that conditional or given probability. Given that you've already taken one card out, it changes the total number of cards in the deck to 51. This is going to be a slightly different number than before because 52 times 51 is 2,652. If you want to actually find out what the decimal is, then it will be 16 divided by that number, 0.006. Just a little bit higher than the previous answer. So the with replacement versus without replacement does slightly change the answer because you're changing how many cards you get to select from. And to help you understand the given probabilities a little bit better, we have another example. A six-sided die is rolled. Let A be the event a number greater than 4 is rolled. So A would only be 5 and 6 as options. Let B be the event a prime number is rolled. Prime numbers would be 1 or 1, 2. I guess 1 doesn't really count as a prime because it has to be divided by 1 and itself. I was thinking odds. So it would be 2, 3, and 5 will count as the prime numbers because primes have to be divided by itself and 1 only. Okay. Now we want to figure out what is the probability of A given B and the probability of B given A. For this, you can actually use the multiplication rule. The multiplication rule says that if you aren't sure if the events are independent or dependent, you assume dependent until you can show otherwise. Then, this rule says that the probability of A given B, if you rearrange the formula, will be A and B divided by probability of B. The one that comes second after the given will move to the denominator of the fraction here. So you just rearrange the formula, divide on the other side, and that's how you can solve for the given probabilities as well, just by rearranging that formula for the multiplication rule. So if I want probability of A given B, it should be the probability of A and B happening over probability of B, the one that's after the given, the bar. Probability of A and B happening is just the number 5. So that's a 1 in 6 chance. The probability of B is a 3 in 6 chance. If you divide the fractions, you'll end up with a 1 in 3 chance. If I do it the other way around, probability of B given A, again on the top, it will still be A and B occurring, but on the bottom, it's always the one after the given, so the A by itself. There's still a 1 in 6 chance of B and A happening together. It's just the 5. The probability of A happening, though, is 2 in 6. So this is a 50% chance, half instead of a third. Notice that the answer changes depending on which probability you have. If you have given B or given A, so you do have to be careful with your given probabilities in terms of which one is written first. Just as a reminder from last class, I also wanted to remind you, without even knowing this formula, you can calculate A given B. Simply what you would do first is you would look for how many elements they share in common, like A and B have one element in common, and then just divide with how many elements the given set had. So it is 3, so it'd be 1 in 3. Whereas for B given A, they share one element in common, but A, what you're given, only has 2 elements to start with, so it'd be 1 in 2. And that's how you can calculate it without using these formulas, but what I wanted to emphasize is they are different answers. So which one you're given has already happened does change your answer. So lastly, in this sheet, I want you to pause to try this learning check. This one's from the textbook. Please do pause the video so you can practice this question before you see the answer. When you unpause the video, I will show you the answer right away. So like always, I hope you tried them on your own. I'll now show you the solution using our probability rules. So the first one is pretty straightforward, the probability of not B. So that'd be the probability of not checking out a book. By the rule of complement, the fastest way to find the probability of not B is to do 1 minus the probability of B. That's 1 minus 0.40, since that's our probability of taking out a book, and that'd be 0.60, or 60%. Then we're asked to find the probability of D and B. This one, we're not sure if the events are independent or dependent, so we're always told to assume dependent until you can prove otherwise. So if you're assuming dependent, then the rule for dependent events is you take probability of B times probability of A given B. So in this case, it'd be probability of DVD given book times probability of book. We're given these numbers in the question. Probability of DVD given book is 50%. Probability of book is 40%. If you use Excel to calculate that, 0.5 times 0.4 will be 20%, or 0.2. This one's a little trickier. Probability of book given DVD. This one, you'll have to solve like we did the previous question up here with the conditional probabilities. That it's the probability that they both occur, so book and DVD, divided by the one on the bottom, or after the given bar, probability of DVD. We just calculated that the probability of book and DVD is supposed to be 20%, and from the question, the probability of DVD is 30%. So 20% divided by 30%, we can use Excel for that. And it's 0.66667, or 2/3. Then we just reverse these to try the probabilities for not book. So probability of DVD and not book, and then probability of DVD given not a book. We'll do the probability of DVD and not book first. This one's a little bit tricky. We'll learn a strategy that can be used to solve this one better in the next sheet. But for now, let me just give you a relation back to that the probability of an entire sample space is 1. We know that the probability of getting a DVD would also be equivalent to the probability that you get a DVD and a book, or you get a DVD and do not get a book. You get a DVD by itself is what that's saying as well. You get a DVD and a book, or a DVD and not a book. The reason that this helps you is you can then rearrange this formula for what we want. DVD and not book, if you rearrange it, would be probability of DVD minus probability of DVD and book. And those are things that we do have the answers for in the question. Probability of DVD and not book would be probability of DVD, which from the question is 30%, minus the 20% that we calculated earlier of DVD and book, leaving you with 10% chance that they get a DVD and they do not get a book. For that, we just rearrange the formulas to be able to solve for DVD and not book. Once we have that answer, then it's a lot easier to get the final answer for probability of DVD given no book. That's just probability of DVD and no book, which we just calculated, divided by the probability of no book, which was our first answer. So 10% divided by 60%, which would come out to 1 in 6, or 0.166667. So those are all of the answers for the library question. This one's from the textbook. It's found at the end of section 3.3 from the textbook practice questions on the section on the multiplication and the addition rule. There's a lot more practice questions in the textbook. I encourage you to try them all because the more questions you do, the more comfortable you'll feel with these formulas. We'll stop this video here for now, and then the next video, we'll finish off with our last learning objective for learning outcome number 3. Thanks for watching.